In this video, we're going to go through one-step stoichiometric conversions. This video is intended for an honors chemistry class. The essential question that we're going to be answering is, how can we use stoichiometric conversions to relate mass, moles, molecules, and atoms of a substance? So let's dig in. So let's just do some math here. You've maybe done this conversion before when you're trying to convert good old imperial inches into metric centimeters. So the question is asking, how many centimeters are in 18 inches? And we know that 1 inch is equal to 2.54 centimeters. So maybe you know that I'm just going to multiply 18 by 2.54 because in every inch there's 2.54 centimeters. All right, so let's pull out our calculator and let's do the math here. So 18 times 2.54. So that's 45.72. So 45.72 centimeters. Okay, let me show you another way to set up that same problem. So again, let's say you have 18 inches. And let's say that you know for every 1 inch, you have 2.54 centimeters. Basically doing the same thing. So I would multiply 18 by 2.54, and I'm going to get the same answer. This is just another way of setting it up. And this in the middle here is called a conversion factor. So it's a fact that we know about the two units, and we can relate them. So let's do another problem. This one says, how many inches are in 36 centimeters? Okay, so I'm going to set it up just like I did in the previous problem with a conversion factor. Okay, so that relates all of the units to each other. So I'm going to start with my given number, which is 36. And I'm going to set up my conversion factor. So notice in the last problem, we started with inches, and then our units of inches went in the denominator, so our units were the same diagonal from each other. This time, we're starting with, not inches, but centimeters. So the units of centimeters are going to go in the denominator. So there are 2.54 centimeters in 1 inch. So the math is going to be a little bit different here. Instead of multiplying, I'm going to divide. So 36 divided by 2.54 gets me 14.17 inches. Well, how do I know it's inches and not centimeters? Well, the question's asking for inches, but I want to show you something. So in the setup here, if you notice, I have centimeters in the numerator right here, and also in the denominator of my conversion factor. These units are going to cancel out. And all I'm left with are units of inches. This seems like it's a lot of work for a really simple problem, but just trust me, you're going to want to start setting these problems up like this. When we get into 2- and 3-step conversions, you're going to have your given, and you're going to have multiple conversions in a row. And I know it seems like a lot right now, but just trust me, it'll make things a lot easier when we get into doing multi-step conversions. It'll help you keep everything straight when you go to multiply and divide. So just trust me, I know this looks like a lot. Okay, so we're going to go through several cases of one-step conversions. We're going to start by converting between moles and grams. And when we do that, we're going to use the molar mass as our conversion factor. So we always start with the given quantity, which is the number provided in the problem. In our last example, our given quantity was 36 and the units were centimeters. And then we use the conversion factors to set up the equation so units cancel appropriately. So we always want to make sure our units are diagonal from each other so they cancel out. All right, let's go through this example. It says how many moles of calcium chloride are in 3.2 grams of calcium chloride. So we're going to start with our given, which is 3.2 grams. And it's not just 3.2 grams, it's 3.2 grams of calcium chloride. Okay. Now, I'm going to use the molar mass. If you don't know how to find molar mass, you should go back and watch my video on how to find molar mass. So I've already calculated the molar mass in advance. The molar mass here is 110.98 grams of calcium chloride. That's how many grams are in 1 mole of calcium chloride. Okay. Now, when I put this in my calculator, if I multiplied 3.2 times this fraction, I would end up with 3.2 over 110.98. And I would just do 3.2 divided by 110.98 to get my answer. So an easy way to remember this, and this only works with conversion factors that have a 1 in them, if your number is in the denominator, like what is here, you're going to divide. If it's in the numerator, you're going to multiply. So it's going to be 3.2 divided by 110.98, and we get 0. Let me write this out, 0.028834024. So we get this really long number. Now, if you recall, we always want to round our final answer to the number of sig figs. So we have we have 2 sig figs in our given. So I'm going to run around my final answer to 2 sig figs. So I don't start underlining until I get to a non-zero number. So that's going to be the 2. All right, so I underline my first 2 significant figures, and then I look at the third digit. So because my third digit is an 8, I'm going to round this up to a 9. And there's my answer. Let's do another one. Let's go the other way this time. So this time we're given moles, and it's asking us to go to grams. So we're going to start with the given. So 6.80 moles of sodium carbonate. Okay, let's set up our conversion factor. So I know that I'm going to need the molar mass. However, the grams can't go down here because the units won't be the same. So I'm going to put my molar mass on the top here. So the molar mass of my sodium carbonate is 105.99 grams. That's how many grams are in 1 mole. Okay. So any number over 1 is just going to be that number. So when I go to do my math here, it's just going to be 6.8 times 105.99, and I get a big number. So let me go ahead and write that down. So it was 720.732. And we're rounding to 3 sig figs this time. So it's going to be 721, and my units are going to be, so these units will cancel out with these units, and I'll just be left with grams. All right, now let's move on to particles. So going between moles and particles. If you remember, Avogadro's number is 6.02 times 10 to the 23rd. That's going to be our conversion factor. So in 1 mole, you have that many atoms or molecules or whatever. A mole is just 6.02 times 10 to the 23rd. So let's do an example. This question says, how many moles of magnesium are in 7.5 times 10 to the 23rd atoms of magnesium? So this is going to be our given here. So I'm going to write that out as awful as it looks. Okay, and I'm going to set up my conversion vector. So again, when we're converting between moles and particles, which in this case it's atoms, we're going to use Avogadro's number. So that's going to go in the denominator. So 6.02 times 10 to the 23 atoms of magnesium. That's how many atoms of magnesium are in 1 mole of magnesium. Okay, now this looks absolutely terrible to put into our calculator, but it's actually quite easy. As long as the power is the same, so in this case it's times 10 to the 23rd, I can cross that off. So now it's just going to be 7.5 divided by 6.02. So 7.5 divided by 6.02, and I get 1.24. So I'm going to go ahead and write that down. 1.245433. And I'm going to round this to 2 significant figures. And then I'm going to look at the next digit. So I'm going to round this to 1.2 moles. That's how many moles of magnesium are in 7.5 times 10 to the 23rd atoms of magnesium. Just FYI, in case you were wondering. All right, let's do another example. This time let's go the other way. So again, we're going to start with our given. This time it's 5.5 moles of water, which is H2O. Okay, so we're going to use Avogadro's number. So if moles are here, remember Avogadro's number is going to be particles. So in this case, it's going to be molecules. So that's going to go on the top of our fraction because the 1 mole is going to go on the bottom. So there's 1 mole of water, and 6.02 times 10 to the 23rd, let's call this molecules of H2O. Okay. Now, this time we don't get to do that little shortcut with things canceling off. So let me show you how to put this in your calculator. So 5.5, all right, times this number right here. So you can type in 6.02 times 10 caret 23, or you can type it in as 6.02 second E 23. That E is the same as times 10, and whatever number, in this case 23, that comes after the E is your exponent. Notice the answer is also given to us in the same form. So the number is 3.311 times 10 to the 24th. Okay, now there is a common mistake that's made when rounding to sig figs with scientific notation. So this is 2 significant figures. So your gut probably says, all right, well, easy. This is just going to be 3.3. Not so fast. We want to include the power here, and don't forget your units. So this is going to be molecules of H2O. So you want to include the times 10 and whatever comes after that. In this case, it's 24. Okay, so that'll be our answer here. All right, not too bad. Let's make it a little bit more complicated. Let's now add in moles and atoms in compounds. So this time we're going to account for the subscript in a chemical formula. So for every mole of a compound, subscripts indicate the number of moles of each element. So let's do an example, and this will illustrate what I'm talking about here. So it says how many oxygen atoms are in 1.5 moles of CO2. Okay, well, let's look at CO2. So in 1 mole of CO2, we have 1 mole of carbon, There's 1 carbon here. And then I have 2 moles of oxygen because it's O2. Okay, so again, we're going to start with the given. So 1.5 moles of CO2. And let's convert that to atoms. Moles are in the numerator, so my 1 mole is going to go in the denominator. Avogadro's number is going to go in the numerator. All right, and we're going to have, these are going to be molecules because it's CO2. Okay, so when I do the math here, I'm going to get 9.033 times 10 to the 23rd CO2 molecules. So a molecule, remember, is made up of several atoms. Okay, but that's not what the question's asking for. It's asking for how many oxygen atoms are there. Okay, so let's do this. So 9.033 times 10 to the 23 CO2 molecules. Now, I know this seems tedious, but every single time I'm writing out what it is. It seems like overkill, but again, it's really going to help keep our units straight. Okay, so for every 1 molecule of CO2, I have 2 oxygen atoms. Or here, let me rewrite that, 2 atoms of oxygen. So I'm basically going to take my number and multiply it by 2, and I am going to roughly get 1.8 times 10 to the 24th atoms of oxygen. So I had to look at the chemical formula to determine that there were 2 atoms of oxygen for every 1 molecule of CO2. Well, that was a lot of work. Oh, we got 1 more. In this case, we're going to go between grams and moles for specific atoms in a compound. So the first step is going to be first converting to moles. So using our molar mass to go from grams to moles, and then using the formula or in looking at the subscripts to determine the number of moles. All right, so in this example, it says you have 50 grams of H2SO4. So that's our given. Okay, so let's convert that to moles. So I'm going to set up my conversion factor, and I know my molar mass is going to be 98.09 grams. You have that many grams in 1 mole of H2SO4. Okay, so when I do the math here, I get 0.5097 moles of H2SO4. Again, it's asking about oxygen, and if you look at the formula, there are 4 moles of oxygen for every 1 mole of H2SO4. So we're going to take our moles and set it up like this. So for every mole of H2SO4, so for every 1 mole of H2SO4, I have 4 moles of oxygen. Okay, so if I do the math here, I end up with 2.04 moles of oxygen. And that's it. So we went through several cases where a one-step conversion is used. I know this was a lot, but again, trust me, these conversion factors are going to be your best friend as these problems get more complicated.